Let's talk real quickly about semiconductors and band theory. Semiconductors are those elements between metals and nonmetals, right? They conduct electricity a little bit, but not as well as metals. How does that work? Well, the atomic orbitals of the atoms in those substances are delocalized over the entire crystal. So in a sense, that crystal is like a giant molecule. And you've got those molecular orbitals. You've got lower energy bonding orbitals, higher energy anti-bonding orbitals. As the number of atoms in that molecule increases, the energy difference between the levels becomes negligible. So that's the idea here. If we're drawing molecular orbitals, here if we had one lithium atom and two lithium atoms, now we've got an anti-bonding and a bonding, and 3 and 4, and as you go more and more lithium atoms in this substance, then the difference in energy between these levels becomes less and less until they form two bands of orbitals. Half of them are anti-bonding orbitals and half are bonding orbitals. The valence electrons will be in the bonding orbitals. So these are the occupied orbitals, and then there's empty ones. And the difference in energy between these is very small. So the valence band where the valence electrons are is typically full, and so the electrons can't move. But if they get a little bit more energy, bump up into the conduction band that's empty, then they can move very easily. So in a metal, there's no gap between the conduction band and the valence band. So this is a conductor such as a metal. Here's a valence band. This is full of electrons. It's kind of like a traffic jam on a freeway. The conduction band is like the shoulder, completely wide open and empty, and you're like, man, it's just so tempting to just drive on the shoulder, right? Why don't you do that? Because what happens if there's a cop? You're going to get a ticket, right? You're going to have to pay a fine, and your insurance rates might go up, and just that keeps you from driving on the shoulder, right? There's a cost. For metals, there's no cost here. There's no energy gap. There's no consequence to driving on the shoulder to get around the traffic jam. So why wouldn't you, right? So they do. Metals conduct electricity because their electrons can move into this conduction band. No energy gap at all. In an insulator, there's a big energy gap here. Insulators are non-conducting things, mostly non-metals. Here, the penalty for driving on the median or the shoulder is huge. Like, you're probably going to get thrown in jail. Like, not worth it. I'll just sit here in the traffic jam, thank you. Right? Here in the middle is maybe a little closer to real life. It's like, well, I might get a fine, but maybe I won't. And so maybe you want a chance. It depends, right? So small energy gap. So some electrons can move up and conduct. This is where we have semiconductors. It's between a big energy gap and no energy gap. And what's very neat about these things is the conductivity of them changes with temperature. So you heat them up, you cool them down, you can cause the conductivity to change. That makes them really useful in a thermometer, right? You can use the conductivity of semiconductor to measure the temperature in something. Any questions so far? Typically, the band gap decreases as you move down a column of elements, which makes sense because we're going from non-metals into metals, and metals have no conduction, no band gap. So looking carbon, silicon, germanium, tin, lead, we see the band gap goes from 5.5 electron volts down to none for lead. And as the band gap decreases, we go from an insulator to a semiconductor to a metal. You can control the conductivity of semiconductors by doping them, mixing them with other things. So you put a little bit of an impurity in there, and you can change the conductivity of the semiconductor. There are two types of semiconductors, N-type and P-type, and it depends on what kind of holes you're making. You can make a positive hole or a negative hole, and this is allowing spaces for the electrons to move more easily. In an N-type semiconductor, we're adding in a doping agent that has more electrons than the semiconductor itself. And so those extra electrons have to be in the conduction band. They've got no choice. Because you have electrons in the conduction band, it's going to conduct electricity better than the semiconductor by itself. So if you take silicon with 4 valence electrons and add a little bit of phosphorus in it, each of the phosphorus atoms has 5 electrons. And so the extra electron that the phosphorus atom has to go into the conduction band. Those electrons are mobile and electrical charge is conducted. Here, the charge carrier is the negatively charged electrons, and then hence it's called an N-type, a negative type semiconductor. In a P-type semiconductor, what we're doing is we're putting in a doping agent that has fewer electrons than the original semimetal. So if we dope silicon with gallium, gallium only has 3 valence electrons. And so if you've got some atoms in there with only 3 valence electrons, you're going to have some holes in the valence band. And those holes can move. So electrons can move into the hole, causing the hole to move in the opposite direction. The holes act like positive charges, and so it's called a P-type semiconductor. And then at the heart of most electronic devices are p-n junctions. So you put these two types of semiconductors together and you can make them do all kinds of cool stuff, and that's why your cell phone works basically. They can act as diodes, allowing current to flow in only one direction. They can act as amplifiers, take a small current, amplify it into a large current. So much of electronics is based on semiconductors and controlling the conductivity. Which element would you dope into germanium to create a P-type semiconductor? Well, P-type, P positive. So if we imagine our conduction band, this is the conduction band and this is the valence band. And here we've got electrons and it's full, right? We've got a traffic jam. In a P-type semiconductor, what happens is we're going to go in there, maybe a helicopter comes across and is picking out a couple of cars from the traffic jam. If I remove this car right here, let's see if I can do that. Now it's going to take the whole line. Let's see if I can remove this one. So if I remove an electron, now I have a hole. This electron can move in here, and that causes the hole to move out the other way. And so the electrons can move because there's a hole. This is essentially a positive hole. We get a positive hole by using a doping agent that has fewer valence electrons than the semiconductor. So here we're doping germanium. Germanium is the base element, and so we want to pick one that has fewer valence electrons. So germanium is in group 4. It's got 4 valence electrons. Indium is group 3, 3 valence electrons. Tin is also group 4, and arsenic is group 5. So which one do we want to use? The indium. This has 4 valence electrons. I'm sorry, 3. Yeah, 3 valence electrons. And so when I mix it into germanium that has 4 valence electrons, I'm going to end up wherever there's an indium atom, there's going to be a hole because of 1 less electron. And that will increase the conductivity of the semiconductor.